We're going to hear about the next generation of dark matter experiments that's planned for the lab. It's my pleasure to introduce Dr. Tom Shutt. Tom actually worked for quite a period of time and one of the instrumental players in the LUX experiment and the work that you saw here. He's now the spokesperson for the LZ experiment, or the LUX ZEPLIN experiment. He's from Case Western Reserve University, and we've asked him to come and talk about the next generation and where we're going from here. Tom?
Right. So you can't read this transparency because I like to put up this beautiful photo that was taken at the surface lab where we got LUX detector first constructed. And what it says is the LUX ZEPLIN experiment. But that was one evening after we'd spent all day working in the clean room. I'm talking about the future, but I thought it would be fun to kind of put our program in context and look a little bit at the history of looking for WIMPs. This is a plot versus time. This is today. This is more or less the start of the field. The idea that WIMPs might be the dark matter, it goes back to about 1985. And this is that size of a WIMP for which LUX is now right down over here. But the very first measurement actually was not the Ray Davis's experiment, but another experiment that was going on right here on site, looking for double beta decay, this kind of odd neutrino process. Repurposed, they looked for dark matter in their data, didn't see it, and set a limit right there. And then that experiment is essentially the maybe the grandfather or great-grandfather of what's now the Majorana experiment. And that's essentially when the field started, and by about 15 years later, the very first results from an experiment that actually a lot of us Luxers had been on came out. And you know, we'd improved things quite a bit, little over an order of magnitude, factor of 10, over those 15 years or so, and we were very excited. And so I want to tell the story. You're hunting dark matter. It's a bit of an elusive quarry. So this new CDMS result came out. This is the same as you just saw for LUX. Now LUX is way down here, but we were very excited to get there. I was a member of this experiment, as was Rick. And the predictions, this colored area is what the theorists thought we would do. And just as a reminder, when you see a curve like this, it means we didn't see anything down here. We couldn't, but we said anything up there is ruled out. Some people actually thought they'd seen WIMPs back then. And the mass here, that 1 atom of gold is about here on the mass scale for how heavy the WIMP could be. So after that came out, some friends of ours in the theorist community said, "Oh, that's great. You guys have spent 15 years and you've done a factor of 10. But really, you should be looking down here." So this is the same curve, slightly different units, but they say, "Okay, it's great you're up there and you went from that line to that line, but guys, you got to go down here." In fact, they were kind of nasty. They said, I guess you can't see this, the colors, let me read it. So their predictions fall considerably below many of the possible predictions in the literature. So then they were talking about these predictions, and may discourage some faint-hearted experimentalist. These detectors were the size of a hockey puck, and we'd spent 15 years getting there. And then they said, "We should not want our experimental colleagues to be too downcast by the long road they appear to have to cover in order to test our models." And really, we've been, since the dark matter game started, there's kind of been this range of models, which in principle has no real bottom end, but kind of is limited to an area down here. And you'd really like to get down in that region. And I first made this transparency back in 2002. And I threw up, because I just got into the xenon game, I threw up this 10-ton projection here, which more or less covers those models. Now, going back to Ray Davis, of course, he was looking for neutrinos from the sun, and you need very large detectors to do that. And there's a class of detector, and oh boy, this is a beautiful photo that's a little bit dark. We're looking at like a 3rd generation solar neutrino experiment. It's about 40 feet across. Oh, there we go. Very nice. And it's kilotons of material. And it's radioactive out on the edges, and the center is just simple fluid that emits light when it's struck by particles. The center of it is about 1 million times lower in radioactivity than CDMS was at the time. In fact, than CDMS is even today. That's this other earlier generation dark matter experiment. And a lot of people in the field started to ask the question, well, gee, can we do a dark matter experiment that kind of has high-techy detectors like LUX, but somehow has got big chemistry getting rid of backgrounds like Ray Davis did and like these type of experiments did. In fact, can we do better living through chemistry? And physicists don't like chemistry, but maybe we got to, roll up our sleeves and learn some. And the answer is indeed yes, and you've seen it today with LUX. And in fact, so this is the progression since then. In blue are actually the type of detector that CDMS was, and it finally, those have gotten to here, but in green is liquid xenon based detectors, and they're LUX, we just added this data point today. But we'd really like to go massive. And how are we going to be massive like those huge solar neutrino experiments for dark matter? And I believe the answer is you're going to start with LUX. So I'm not going to go through it again, but this design has all these wonderful properties about recognizing the event, telling the difference between background and signal, et cetera, et cetera. You've heard all about this wonderfully from Dan and Rick. We're going to make it bigger. So there's a photo of LUX in a drawing of LZ. It's 3 times in each dimension. 3 cubed is 27. It's a much bigger detector. We also want to measure every bit of radioactivity. We're going to surround LUX with an active scintillator. So this is this thing outside is in itself like an experiment. Is like an experiment like that solar neutrino experiment. Is a detector like that solar neutrino detector. It's made out of liquid scintillator. And we're at the point now where all the radioactivity associated with these experiments, anyway, the radioactivity that comes from materials is all at the periphery. And if you surround it with a hermetic detector, you're going to sort of know any time there's a bit of radioactivity. And you're going to be definitively clear if there's events in the center that they're not from that radioactivity. So that's sort of how we're going to approach sort of a marriage of the earlier dark matter experiments and the really large-scale neutrino experiments. And so this is LZ. It's the same LUX water tank that was designed on purpose to be big enough to handle a next phase experiment, and now a greatly enlarged detector and the scintillator shield. A high voltage system, which is much upgraded from the one we used in LUX, and cartoon people. So LUX was a dry run. Well, that's a terrible title. First off, LUX isn't was. Secondly, LUX is in water. Thirdly, most evenings after people worked on LUX, they went to a bar. But LUX, in terms of LZ, LUX was a dry run. So there's all these technologies. In fact, when we planned LUX, we wrote down that a reason why we're doing LUX is to prototype the technologies that we need to do a very large experiment. So putting it in a water tank, titanium vessels, cryogenics, I could go on and on and on. Let me tell one story about putting it in a water tank. Dan and Rick and I were all in an experiment, a precursor of LUX called Xenon 10. And in an early, in fact, several of the people in the room were in that experiment. In an early day, in fact, when we were first thinking about where shall Xenon 10 go, Rick and I were over in Italy looking at a site. In fact, and we were looking at the water tank where Borksino is. Borksino's in a water tank. And I looked at it and I said, we got to put a xenon detector in a water tank. And not everyone agreed. Rick and I thought, that is the thing to do, but how are we going to do this? And then a year or two later, Rick came and said, Tom, we got to put it in Homestake. And we called up Kevin, and well, kind of the rest is history. I also want to credit, we're joining forces with Zeppelin. That's why it's LZ, LUX and Zeppelin. Zeppelin was a British and American experiment. In fact, LUX already had people, the American team from Zeppelin. In fact, the Zeppelin folks did the first liquid xenon experiments. So back on my slide where I said the liquid xenon stuff, this team really they were the ones that started the field. And in key areas, they've done sort of better than anyone else. And so the team now, well, it's LUX and ZEPLIN. And in addition to, of course, all these technical things, I think we really have a tremendous collaboration. And tremendous collaboration with the lab. So what is this collaboration? Well, it's a lot of groups now. A little bit bigger than LUX per se. These are the US groups or institutions, including SDSTA here. 9 overseas, now a Russian group. So 9 US and 9 international institutions. A lot of people would like to find dark matter. I mean, this is a measure of how interesting it is to scientists. It's going in the Davis cavern. What should you take away from the slides? Well, first off, that the planning is fairly advanced. Second, it barely but fits, okay? It's sort of a, I don't know how many potatoes in a certain size bag or something, but it's some homily there. But it works. An interesting point about it is it's going to be a neutrino-dominated, it's going to be an experiment where the dominant background is neutrinos. This is a map from simulation of what we should see as backgrounds. I think it was Rick, I think, showed the background in LUX, and it looks similar to this, but that was data. This is, predictions. This is all the terrestrial backgrounds. They're sort of around the perimeter. This is R, this is depth, distance out from the center. When we turn on our scintillator veto, we get this nice quiet region in the center. Almost 6 tons out of the 7 essentially will be quiet. Quiet, well, they won't have any radioactivity, but they're going to have neutrinos. Neutrinos are going to be the ultimate limit to WIMP searches. So 40 years ago, detecting a neutrino from coming from astrophysics was a big deal. It still is. They're going to be a nuisance signal for us. They're coming from the sun. They're coming from cosmic rays striking the atmosphere, produces reactions, and neutrinos come down. So we can go underground to get rid of cosmic rays, but you can't get rid of neutrinos. To stop a neutrino takes a light year of lead. And actually there's a neat piece, which is all the supernovae that have gone off throughout the history of the universe. And these 2 pieces, there's just nothing you can do about them. And they're going to, we predict in LZ about almost an event. The neutrinos from the sun look like the electron recoil backgrounds you just heard about, and we can reject them, at least most of them. Let me tell one other story. I mean, you always, science from the outside, it looks like, all these people, just writing papers and doing their thing. There's kind of a human side, and I want to tell a human side. It just happens to be a story about krypton removal, but it's really about people. So here's the Ray Davis experiment, and there's Ray Davis, and behind him you see all this chemistry apparatus. He was actually a chemist. So the homestake experiment, which the dates here say 70 through 94, because that's what Wikipedia says. They had was 600 tons of cleaning fluid, and they extracted a few atoms of argon from the cleaning fluid using chemistry. And for years, no one believed him because physicists thought there is no way and you can possibly do that. But there's this long history of chemists leading the way on understanding radioactivity, and that's what's needed to do things like this. People that worked on this experiment did a later generation dark matter experiment that was, solar neutrino experiment that was at Gran Sasso, the Italian site. And there, they did a similar stunt. They extracted neutrinos turned gallium, which is this liquid metal that's very exotic, kind of like mercury, but way expensive, into a few atoms of germanium, and they pulled germanium out of gallium, which is incredible, and this is some chemistry drawing. And then later, Borexino happened with some of the same people that worked on that experiment. And in Borexino, radon had to be removed from air and nitrogen and fluids. And these chemical techniques sort of were handed down from people, from Ray Davis to people that worked here, to people that worked there. And then we learned those techniques and applied them to remove krypton from radon. And now that's going back in the Davis cavern. So it's kind of a nice, so they say intellectual parented lineage of a technique used in LUX and LZ goes back to Ray Davis. So what would the sensitivity of LZ be? Here's the same, size of the WIMP and mass of the WIMP, and below the lines is ruled out. So here's where LUX has gotten. Well below those, my first thing I showed with CDMS up there. LUX should get another factor of, say, 4, maybe 5. But LZ in a 3-year run will be about 1,000 times past where LUX is now. Maybe with a 6-year run, we might get another factor of not quite 2. These atmospheric neutrinos are kind of setting a floor, which is a bit beyond LZ, but not a lot beyond LZ. So we're going to be approaching that neutrino background. So I have just a couple slides left. So what's the timeline? So now I'm showing you sort of our full solid points I've shown before. They're actual things that exist. Circles are sort of things that people are talking about, okay? So this is where we think LUX will get and around when it will get there. And this is what we think LZ will do and around when it will do it. So specifically, the agencies, back here, dark matter is a very competitive field. Everyone wants to find the dark matter. There's a lot of experiments. This is color-coded by technology, but there's many more than 3 or 4 experiments in here. And it's gotten to a scale where we just can't go on with a huge number of technologies. And the agencies are conducting this is, I guess, a NASA term, down select. And so that means there's a bunch of us that go into the gunfight, and then some people are selected and some people are down selected. And we want to be selected. So there's a proposal which we've been busily working on. The combined LUX-LZ set of people are kind of schizophrenically been trying to get LUX done, and then there's some people and other people focusing on the proposal for this down selection. So November 26th it's due, and we're expecting a decision from the agencies in January. And then if we are selected, the sort of project really starts to turn on after we do this so-called CD1 in April, and the completion currently, if things don't slip, is projected for March of 17, and that limit is compatible with us getting to there before the turn on and then running 3 years. Of course, the field isn't sitting still. I just showed LUX and LZ points. Here's the other points of what other people are expecting to do. There is one similar experiment to LZ, a very similar one, that is funded and may and presumably will turn on and get a bite of the apple before LZ does. So we're here, and LUX can get to there. These guys may get here, we'll see when, and we'll get down here and we'll see when. But we think we have the experiment, the site, the collaboration, and in particular the partnership with the lab, which goes back to the site, but the partnership with the people to succeed. And if we do, the combined set of experiments, LUX-LZ, are going to be the ones to beat for most. There's going to be a leapfrogging thing, but most of the next decade or more. And in this range, we're going to hope to see the dark matter. That's all.